we start the lecture. Union and intersection. Oh. Sorry, I must share the screen first. Okay. So let me share the screen first. Yes, I'm sharing the screen. Union and intersection. Union and intersection. Okay. Firstly, we define union. Definition of union. The union of two sets. The union of two sets. The union of two sets A and B is denoted by and is defined as A union B, and this is A union B and is defined as this A union B is X belonging to X such that X belongs to A or X belongs to B, right? So if we see the Venn diagram of A union B, that is A union B is the whole set. The shaded portion is A union B is A union B. Numerically, look at that. If A is 1, 2, 3, 4 and B is this 5, 6, 7, right? And the A union B is 1, 2, 3, 4, 5, 6, 7. That is this. We can take if A is this 1, 2, 3, 4 and the B is 3, 4, 5. Then the A union B, because here the disjoint means A is the elements are A are not in B and means are B are not in A. But if they have the common elements, in that case the A union B is 1, 2, 3, 4, 5. We will not repeat this 3, 4, right? So A union B is X belongs to A or X belongs to B or X belongs to both. Right? This can be possible because you can see in the Venn diagram there are some elements which are in A as well as in B. You can see here, right? So that is the shade, means this is a, we can say is a universal set. The shaded portion is this A union B. A has some elements, B has elements, and there are some elements which are common in between A and B. So what are these common elements? These are the intersection of A and B. So now we are coming to the definition of intersection. Right, next definition of intersection. The intersection of two sets the intersection of two sets. The intersection of two sets A and B is denoted by this A intersection B and is defined as X such that X is in A and X is in B. Right? It is defined in this manner. Means what is here? This, if in the Venn diagram, you know well, because we have discussed we have discussed now that what are the common elements. This A, this is B. So this shaded portion is A intersection B. This is common between A and B. Shaded portion is A intersection B. A intersection B means common elements between A and B. Right? So you can see that this A is this 1, 2, 3, 4 and B is this 3, 4, 5. Then the A intersection B is 3, 4. Right? While A union B is 1, 2, 3, 4, 5. Now we will discuss if there is no common element between A and B. If there is no common element between A and B, then A intersection B is empty set. You can see this if A is 1, 2, 3, 4 and B is this 5, 6, 7, right? In this case, A intersection B is empty set. We have no common element between them. A intersection B is empty. Right, now we are coming to the disjoint set. Right, two sets A and B are disjoint if they have no common element. Right, so we can write disjoint sets. Two sets are disjoint. Two sets A and B are disjoint if A intersection B is empty. So these two are disjoint sets. Right, now we are coming to the pairwise disjoint set. Pairwise disjoint sets. That is a family. Now instead we have a family. Instead of A and B, we say A1, A2, A3, right? So a family AN of sets is said to be pairwise disjoint pairwise disjoint is said to be pairwise disjoint if AI intersection AJ is empty, right? For all I and J, and I is not equal to J, because if I is equal to J, then AI intersection AI is AI. It's not, it cannot be empty. So for all I and J are not equal. That is a pairwise disjoint. So we have discussed intersection, the complement of a set. Right? Now we are coming to the complement of a set. This complement of a set is denoted by complement of a set is denoted by AC or sometimes A prime, right? So it is this, the complement is, and it is defined as X such that X does not belongs to A, right? So that means those elements which are not in A are in the complement of that. So according to the Venn diagram, if we see the Venn diagram, right? This is AR, this is RA, this is RA, but these elements are not in A, right? These are not in A. So that means this shaded portion is the A complement. Is A complement. If we say the universal set, means if we take X that has the elements 1, 2, 3, 4, 5, 6, first 9 numbers we can take, and the XA has this 1, 2, 3, 4. Then the complement of A is 5, 6, 7, 8, 9. This is A complement, right? So those elements which are not in A. And you can see that A union A complement is the universal set, right? A has 1, 2, 3, 4, A complement has 5, 6, 7, 8, 9. So we combine them, we get our universal set. This is what is universal set, right? A complement is also written as, now we write the difference. Before defining this, we define the difference of the elements, difference of the sets. Difference between two sets. Difference between two sets, or difference of sets, right? The difference A minus B. Difference A minus B, difference A minus B between two sets the difference of the two sets is denoted by two sets is denoted by A minus B or B minus A, and it is defined as A minus B is the elements which are in A but not in B. Right? This is A minus B. And like if we have A as this 1, 2, 3, 4, and B has this 3, 4, 5. So elements which are in A but not in B, then A minus B is just 1, 2. B minus A is X such that X belongs to B and X does not belongs to A. So if we consider this example, then this B minus A is the elements which are in B but not in A is just 5 only, right? If we consider this example. Okay, so that is the difference. If we see here, we have the complement x such that x does not belongs to A, right? So that means we can write this complement as universal set minus A, means x belongs to x and x does not belongs to A. So this is x belongs to x such that x does not belongs to A. This is a universal set, right? So this is what is here. Now we are coming to this. After complement, we are coming to the symmetric difference of sets. Symmetric difference of sets. Symmetric difference of sets, right? The symmetric difference of two sets. Difference of two sets A and B is denoted by this or this, right? And is defined as x belongs to B, x belongs to A and x does not belongs to B, or, right, x belongs to B and x does not belongs to A. We can say this is x belongs to this or this. So that means the difference of the two sets is this is A minus B union B minus A, right? Now this is what is similarly this B is B minus A union A minus B. A minus B. Means x belongs to B and x does not belongs to A, or x belongs to A and x does not belongs to B. This is the symmetric difference, right? Right. So if we have A equal to this 1, 2, 3, 4 and B is 3, 4, 5. 3, 4, 5. Then the A minus B we know is just 1, 2. B minus A is just 5. Then the A symmetric B is 1, 2 and 5. Similarly, the B symmetric A is 5, 1, 2. So you can see these two are equal. These two are equal. Thus A symmetric B is equal to B symmetric A. B symmetric A. Now we are coming to the properties of this properties of intersection and union and intersection. Properties of union and intersection. And intersection. Okay, so let's let A, B, C be any sets. We are given. Then the first property is A union B equal to B union A. It's a commutative law. This union satisfies the commutative property. Right? So you know well, if A is this 1, 2, 3, 4 and B is this 3, 4, B is this 3, 4, 5. Let me see. This is stuck. Oh, I am taken a new base, so I will be less classification of sets. This is not deleting. It's just properties, and now we are coming to this. Just wait. Yes. Just wait. Let me see what example I have taken. 3, 4, 5. Okay. Well, so this is the same example I want to take here. So this is 3, 4, 5. 3, 4, 5. So you can see this A union B is 1, 2, 3, 4, 5, and similarly this B union A is 1, 3, 4, 5, 1, 2, 3, 4. The same, right? These are equal. But how to prove mathematically? That's matters a lot. We see let X belongs to A union B. That X belongs to A union B. That means X belongs to A or X belongs to B. But this OR is commutative OR. So we can write this X belongs to B or X belongs to A. That means this X belongs to B union A. But X is arbitrary. It's an arbitrary element of the universal. So this means that A union B is contained in B union A. But if X belongs to this B union A, then X belongs to B or X belongs to A, or is again commutative. That means X belongs to A or X belongs to A. That means definitely we get X belongs to A union B. That means this equality, this containment converts it into equality. Right? So that is the commutative property in intersection. Similarly, the commutative property in intersection. This is a commutative property in union, and now we are coming to the commutative property in intersection. Right? So that means A intersection B equal to B intersection A. So you have the example that has the elements A has 1, 2, 3, 4, and B has 3, 4, 5. Right? Then the A intersection B is 3, 4. And similarly, the B intersection A is 3, 4. Right? Now, in the similar manner, in the similar fashion, we prove that the A intersection B is B intersection A. So let X belongs to this A intersection B. Means X belongs to A and X belongs to B. So and is commutative, so we can write X belongs to B and X belongs to A. That means X belongs to B intersection A. If X belongs to this, we have this, we have this. Means, and X is our arbitrary element. So this means that A intersection B is equal to B intersection A. If the reverse is not possible, we can't write equality. Now we are coming to the associative property in union as well as in intersection. Right? A union B union C is equal to A union B union C. That is the associative law. Let X belongs to A union B union C. That means X belongs to A or X belongs to B union C. That means X belongs to this A or X belongs to B or X belongs to C. This or is our associative. We can club these two. So that means this X belongs to A union B or X belongs to C. And this gives us that this X belongs to A union B union C. If we have this, we have this, we have this. Now in this time we club these two. X belongs to B or X belongs to C. So that means X belongs to A or X belongs to B union C. And which gives us that X belongs to A union B union C. But this X is arbitrary. And this means that A union B union C is equal to A union B union C. Similarly, the intersection satisfies the associative law. So we are coming to that. A intersection B intersection C equal to A intersection B intersection C. Right? Let X belongs to A intersection B intersection C. That means X belongs to A and X belongs to B intersection C. And that means X belongs to A and X belongs to B and X belongs to C. That means now we can club these two. That means X belongs to A intersection B and X belongs to C. And that means X belongs to A intersection B intersection C. And the X is arbitrary. Right? If we have this, that X is an element of this, A intersection B intersection C, that means X is an element of A intersection B and X is an element of C, means X is an element of A and X is an element of B and X is an element of C. That means X belongs to X is an element of A and X is an element of this B intersection C. Right? Now we club these two, and which means that X is an element of A intersection B intersection C. And since X is arbitrary, means this is contained here. Now if we are taking the reverse, then this is contained here. And this means that A intersection B intersection C equal to A intersection B intersection C. So that proves this property of associative law, means intersection satisfies the associative law. Right? Now we are coming to the De Morgan's law.